Hello, hello, hello. Hey, Katie, how are you doing today?
I'm great, Mac. How are you doing?
I'm doing fantastically. And hello to everybody joining us on the stream.
Yes, hello, welcome, and thank you for coming to our first ever live stream for GCSE Computer Science students. I'm Katie. I'm a program coordinator for Isaac Computer Science. I do all sorts of things, checking things on the website, making sure everything is working properly for you. Mac.
And I'm Mac. I'm a learning manager. You'll find me creating the images and videos across the site, bringing the content to life, as well as writing a little bit of content where I can.
At these live streams, we're going to be covering the computer science concepts that feature on exam board specifications for GCSE Computer Science in England and Wales. It doesn't matter what exam board you're taking, these live streams will have you covered.
Absolutely, we're going to cover them all. In each of these sessions, we're going to be joined by an expert guest speaker to take us through a computer science concept in depth. You'll have the chance to ask the expert questions about anything you found tricky or anything you'd like more information on. Use the chat function on YouTube to ask your questions or the question form on the banner below. There it is. So get your questions in there and we can ask them to our guest speaker.
I'm back.
You are.
Hello. So at the end of each, we had the question banner.
We have.
Excellent, thank you. Sorry about that. At the end of each live stream, we will share an Isaac Computer Science game board featuring some of the questions from the Isaac Computer Science platform for you to try out what you've learned. For this first school term, our sessions will focus on concepts in the computer systems topic, giving you the building blocks of computer science as you start your GCSE studies.
That's right. Throughout autumn term, we're going to be covering things like hardware and software, processors, and so much more. To start with, we're going to be looking at Boolean logic. So without further ado, let's bring on our first guest speaker, Alan Hurd. We've got 16 people waiting to hear from you, Alan.
Hello, Alan, how are you doing?
Very well. How are you doing, Alan?
Fantastic. This is great. Really excited to be on our first live stream.
Amazing. Alan here is a learning manager at Isaac Computer Science, and he has written lots of the GCSE content on the site and the Boolean logic content on the site. So he is the perfect person to take us through the Boolean logic gates today, a famously tricky concept to grasp.
Alan, welcome to the stream.
Thank you very much. Good to see you.
Alan, you've been writing materials for Isaac Computer Science, but I believe you're also a little bit of an electronics expert as well.
Yeah, a little bit. I'm an ex-computer science teacher too, and I now look after the GCSE team, creating the Isaac Computer Science content for this platform. I tinker around in this shed and pretty much fix anything from, I don't know, mobile phones to hoverboards.
Sweet. Good to have a good grasp of electronics. We don't get shocked while we're doing that, isn't it?
For sure.
I have a question. How fundamental is Boolean logic to computer science?
Well, computers are filled with integrated circuits that need voltages to function. This voltage is either on or off, as in when you turn a light bulb on. In computing, Boolean expressions produce a Boolean value when they're evaluated to true or false, either on or off, essentially. This is equivalent to on or off. So everything is represented by either a binary 1 or a 0, which again is equivalent to true or false, on or off. So all the actions that are performed by a computer are dependent on the electricity used, and the Boolean logic determines the state.
Cool. So yeah, quite fundamental then. Well, I'm very excited to hear what you have to share with the viewers today. We've got 22 people. Thank you for joining us. Alan, take it away.
Fantastic. Thank you. Well, I guess the first thing we need to talk about before we start talking about logic gates, I just want to mention 3 words to kind of give some context to what we're going to talk about. So those three words are and, or, and not. So for instance, you might say, I have not done my homework. Or equally, you could say, I have done my homework and I've handed it in. Lastly, you might say, I've done my homework, or I've done some kind of assignment. So the way we use and or not in these sentences allows us to determine what is true or false, whether we've done our homework or not, or handed it in. It's the same principle with these logic gates. So let's get into the first logic gate and have a look at the symbols. So this logic gate that you can see on the screen now, this is a not gate. So a not gate has only got one input, which is A, and it's got one output, which is Q. So when we're talking about these zeros and ones and these inputs and outputs, if we were to enter a 1 into A, 1 as the input, then the opposite would come out, which would be a 0. And equally, if we were to enter a 0 into the input, the opposite would come out, which would be a 1. So that's the simple not gate with one input and one output. The way we can represent this and kind of look at it and find out where we would get a true output, which is kind of what we're basically interested in all the time in computer science, where the output is a 1, we can use what's called a truth table. So you can see the truth table there with the labeled inputs and labeled outputs, and it shows you every single combination. So for this one, there's only a 0 or a 1 that can be input to A, and it shows you the corresponding output, which is the opposite for a not gate. Let's take a look at the next gate. So this one is an and gate. So thinking back to our and statement where we said, I've done my homework and I have handed it in. Well, if both of those things were input into here, the output would be true. This one's got two inputs, which is A and B, and it's also got one output that is Q. So for Q to be a 1, we'd have to have A and B as a 1 going into this and gate. If either of them was a 0, then the truth wouldn't matter. It wouldn't occur because one of them is a 0 and that wouldn't count. We can see that in the truth table. This truth table's got more rows, obviously. Here we've got more combinations, possible combinations of 0s and 1s. So if both of them were a 0, it would be a 0. A 0 or a 1 be a 0. And it's only ever a 1, like I said before, when both inputs are a 1. And these truth tables are fairly standard for these gates. And as we get more into this topic, you can these truth tables can become a little bit more complex, but can really help you determine what's going on with your circuitry. Let's take a look at the next one. So this is an OR gate. Looks a little bit similar to an AND gate, just got a curved bar at the left-hand side instead. Again, two inputs, A and B, and one output Q. So this one's a little bit different in the sense that either one of them can be a 1 for Q to be a 1, or both of them can be a 1. So let's take a look at the truth table. We can see here that 3 of the rows, the output is actually a 1. So where we can see B is a 1, A is a 1, or A and B are a 1. So it doesn't matter which one is 1, long as one of them is there, then the output will always be a 1. And finally, we've got the XOR gate. So this is similar to the OR gate, but the X stands for exclusive OR. And just like the OR gate, it's got two inputs, A and B, and an output that's Q. Okay, and the truth table for this, if we pop that one up and have a look, you'll see that the bottom row now, if we've got both inputs as a 1, the output is now a 0. So it's got to be exclusively one or the other. So either A or B, but not both. So they are the basic logic gates that form the fundamentals of Boolean logic.
Amazing. Thank you, Alan. So these logic gates apply both to electrical voltages and whether or not somebody has done their homework.
Exactly.
Amazing. What powerful things. So these logic gates, where might we see them in real life? Like, what actually are they?
So we see them in real life in the circuitry as far as making decisions are concerned for a computer, but we can use them in programming and use the concept of Boolean logic within our programs too. So I've got a little example I can show you.
Cool. Yeah, take it away. I'd love to see it.
Well, let's take a look at this taking care. So right here, look, I've got Snake here. Look, this is a live Snake on. This is her first appearance on the internet. This is Slytherin, so she's quite happy to be here. And Slytherin, she needs an accurate level of temperature and an accurate level of humidity. So to look after a snake, these are the two things that we really have to be careful of. So to control temperature and humidity, we have two things. We have a heater and we have a fan. So the temperature and humidity, for instance, are our inputs, and our outputs would be the heater and the fan. And if it's too hot in here, I would turn the fan on, and that would bring the heat down. And if it's too humid, so humidity is how much water vapor there is in the air. If I need to reduce the humidity, I'd also put the fan on, because that can circulate the air around and make it less humid. Equally, if it's too cold or too hot, I can turn the heat on or off, because they need a certain level of heat to survive, but not too much. So if we were to look at some examples of this, we would see that you can see on the screen there, the example of the heat that they require is between 25 and 27 degrees, and a humidity of between 40 and 60%. Okay, so 40 and 60% is probably around what it is in a house generally, but it can go obviously higher depending on what's going on. She's crawling at my arm, which is fun. There we go. So with those temperatures and humidity details in mind, thinking about those gates again, the first one was a NOT gate. I could write a program, and I have wrote a program to control the gadgets in here to keep her cool and comfortable. If the temperature is not greater than 24, then turn the heater on. So that's quite straightforward. It's just using the NOT gate. So anytime it falls below 24 degrees, then the heater's going to come on to keep her nice and warm. Equally, on the next one, we can use the AND gate. So in my code, I've got if humidity is greater than 60% and the temperature is greater than 27, then the fan must be turned on, because whether it's too hot or too humid, that fan needs to be on either way. The other way I could do that is with the next one, which is an OR gate, which we saw. So I could say if the humidity is greater than 60% or the temperature is greater than 27 degrees, turn the fan on, because either way, the fan needs to be on to keep her nice and cool. And using these lines of code in this way, we can set the program up to do these things automatically for us. And the next one, there we go. So looking at these logic gates, we've looked at the gates individually, and these can be combined later on to produce more complex and more interesting circuits to get really specific results depending on what you're looking for.
Amazing. So we've got the basic logic gates, NOT, AND, OR, and how do you pronounce that last one again? The exclusively one? It's
pronounced XOR, which stands for exclusive OR, but generally XOR.
Okay, cool. Right, XOR.
So definitely not XOR, like xylem or xylophone.
No, definitely not.
Can you tell us why it's called Boolean logic?
Yeah, sure. Back in the 1800s, there was a gentleman called George Boole, and he came up with a type of linguistic algebra known as Boolean algebra. And the three basic operations of this algebra were AND, OR, and NOT. And he saw these as the only necessary operations to perform comparisons of things.
Cool. So like you did earlier when we were talking about the homework, and you combine those statements to say what would be true, right, with the ands and the ors and nots. Exactly. Okay, cool. And then that got applied to computer science, which is how they make decisions.
Exactly.
Amazing. Thank you so much. Now, the other question is, how do we actually link up those logic gates that we saw earlier? Because we saw that more complex diagram. When will we be covering that?
We're going to do that in the next live stream. And basically, the diagrams that are the gates that you saw, we can just join them together. So the output of one gate essentially just becomes the input of the next gate, and we can follow the inputs through until we get an actual output.
Cool. Right. Well, I'm very excited to hear more about that in the next one. If you guys have any questions you'd like for Alan, please post them in and use the question link, as you can see below, rpf.io/IsaacCSLive-questions. One of my questions I had, Alan, was we went from the logic gates with your voltages, where you had the ones and the zeros that were being read, and then we looked at a program. How would you turn those statements of greater than or less than into a 1 or a 0? To feed into a logic gate? Is there a way of kind of doing that mechanically using electronics of some kind?
So when those statements are evaluated, it will actually return either a true or a false. So when we say if humidity is greater than 60 and heating is lower than whatever value it may be, then each one of those parts, the humidity is greater than, temperature is greater than, they will actually evaluate to a true or a false value, just like when it said at the beginning. So it's either true or false, yes or no, 0 or 1. And it's that 0 or 1 that determines what is going to, the true or the false, that determines that what's going to happen with those devices or what's going to happen in the program.
Amazing. Right. Okay, I see. So those statements are evaluated and they would be true or false, and then that's what feeds into the logic gates. Amazing. Right. That makes sense to me now. Thank you so much, Alan.
You're welcome.
And we've actually got a question from our audience. Thank you very much. So the question from the audience is, can XOR come into Python? So can you code XOR into Python?
There isn't a specific XOR function in Python, but with the way you would do that, if you wanted, let's say, you wanted temperature to be greater than 26, or some, and then what you then do then is not the opposite of something different. So you would still join them up as and ors, but you would, the way you would join them up and bracket them out, you could actually program an XOR, but there's not an XOR keyword like there is an and or not. So you just have to be a little bit smarter the way you program it. So, but there's not a specific one in Python.
Right. So there's not an operator like the other ones. You'd have to make it yourself to get the logic yourself, that you
yeah. And later on in the future streams, there's a couple of other gates, such as NAND and NOR, what people might have heard of. And again, they're just modifications on the basic ones that we've already discussed.
Cool.
Brilliant.
Thank you so much for that question. That was great.
Thank you.
Cool. Well, if you guys have any more questions, make sure you pop them into that YouTube chat so we can ask them to Alan. Any of the gates, any of the other scenarios you might want to hear about. So you said you actually used this logic to code your snake enclosure. So how have you done that? Like what bits of hardware have you used to create that enclosure in this logic?
Yeah, so what I use is a Raspberry Pi Pico microcontroller, and that's hooked up to a small humidity and temperature sensor that's actually inside the vivarium, and that takes readings every 10 minutes. And should those readings go outside the boundaries of where we need heat or humidity, or we need to adjust something, then that sends a signal to an online service called ThingSpeak, where the data is logged, and that in turn activates smart plugs in the house to turn the plug on or off for the heater or the fan.
Cool. Okay. It's really cool to see the sort of Boolean logic that we're talking about applied in real life and used in, using some electronics that hopefully people have heard of as well, Picos and Raspberry Pis. Yeah, that's really, really interesting. Thank you, Alan.
And the snake looks to be doing pretty well. It seems you've obviously got that environment right for it. It seems pretty happy.
Absolutely. Yeah. It was born for the screen. It's moment, and it is showing off. It's very beautiful.
Stuff.
And you've handled it very well as well, I think, letting it roll across your fingers. Amazing. Well, it looks like we haven't got any more questions from the audience. If you guys do have, you can pop them up. Maybe we can bring Alan back on to do them. But in the name of not watching us stand here silently, I will say thank you so much for joining us today, Alan. It's been great having you on, and I really look forward to seeing you for the next one where we do some more complicated logic circuits and we can hear more about how the snake is doing.
Thanks, guys. Take care. Bye.
See you later, Alan.
Brilliant. I feel like I've learned some things there today.
Yeah, me too.
Okay, good. If nothing else, the snake's pretty cute. So, if you want to test what you've learned today, we've put together some questions for you on one of our game boards. The link is there now, so you can type that into your computer and test yourself on those questions.
And don't worry, if you find any of them tricky, all of the questions on Isaac Computer Science have helpful hints to guide you to the correct answer. We also have loads of amazing materials for you to learn more about Boolean logic, plus loads of other computer science concepts.
And in case we haven't mentioned, all our materials are mapped to the exam board specifications for AQA, OCR, Edexcel, Educast, and WJEC to make them directly relevant for your GCSE studies. And that's it. That's our first GCSE live stream.
If you guys enjoyed... Oh, sorry, I've had one more. Before I do the sign off, we've had a cue from the audience, which is when is the next session? And it will be coming in September when school goes back. Make sure you keep an eye out for that. And if you've enjoyed today's session and you want to hear more about the future ones as well, make sure you like and subscribe to our YouTube channel, our Facebook, Twitter, and Instagram accounts, where you'll get all the news about our upcoming live streams and other features. In that session, when it is in September, we'll be continue to explore more about Boolean logic, looking at circuit diagrams and truth tables, which we heard Alan talk about. Yeah, and if you want more information about the live stream events, head over to the event page on Isaac Computer Science. It should be at the top there.
Excellent. Can't wait. So please do let us know how you found today's session by filling out the feedback form below. It'll also be sent out to you later today. We're really keen to make sure that our live streams are really helpful for you. So we really want to hear your feedback and any ideas of suggestions or topics that you would like us to cover. So that's it, folks. Enjoy the rest of your day and we'll see you next time.
See you next time. Thank you so much. Have a great day, guys.